what we've been doing for the past few lectures is bounding these like extremal numbers, right? So remember EX and H, maximum number of edges in a graph on n vertices, which doesn't have a copy of H. And today, okay, so we looked at before we looked at the Erdos-Stone theorem and Turan's theorem, which were, gave a really good answer for these extremal numbers for graphs which are not bipartite. And last time we looked at complete bipartite graphs. Today we're going to look at a different class of bipartite graphs, which is the even cycles. So CM, is a cycle on m vertices. So C4 is just like this, take 4 vertices, put them in a cycle, and so on. Okay, so we want to kind of understand, the growth rate at least of the extremal number of cycles. Okay, here's a kind of quick kind of aside, I guess, that this Kováry-Sós-Turan theorem that we saw last time, it gives us a bound on this extremal number because, if you have a graph and if it has a lot of edges, so if it has more than, say, some constant times n to the 2 minus 1 over k edges, then by Kováry-Sós-Turan, we know that it has a complete bipartite graph where the parts are of size k. Both parts are size k. And of course, like if you have a complete bipartite graph with parts of size k, then you also have a cycle of length 2k because you can just find it inside of the complete bipartite graph. Is that clear? So that implies certainly that the extremal number of this thing is at most the extremal number of that thing. In particular, in general, if you have a subgraph, like h is a subgraph of h prime, then the extremal number of h is less than or equal to the extremal number of h prime, because that's just because finding a copy of h prime will give you a copy of h. Maybe I'll write that in general. So here I'm using subset to mean subgraph. So in general, and this is, I guess, kind of a trivial observation, but that's what we're using here. And yeah, today what we're going to show is that this bound is really pretty poor. So as k gets larger, this becomes closer to n squared, so it becomes larger. But we're actually going to show that the extremal number of a cycle of length 2k, as k gets larger, it gets smaller. Well, or at least we're going to show that the upper bound gets smaller. As with all of these bipartite problems, we're not going to really have good lower bounds, but we'll just have upper bounds. Any questions? So let me now state a theorem of Bondy and Simonovits. So their theorem says that for k at least 2, the extremal number of a cycle of length 2k, so for n vertices, is big O of n to the 1 plus 1 over k, so there's big O, right? That means up to a constant factor, it grows like this. So this is like as n is going to infinity, it grows like this. And I just want to make it clear maybe that the constant here is a function of k. I think in their original paper it was like 100 times k or something, but I might be mistaken. And now since their paper, so I think this was from the 70s or something, people have whittled down the constant factor here. I'm not sure what the record is now, but I think it's about 6k or something like that. I'm not exactly sure. Okay, so you can see that as k gets larger, the exponent here gets smaller, right? So for k equals 2, like this, what this says is that if I look at C4, it's big O of n to the 3 halves, right? If I look at C6, this says that it's big O of n to the, 4 thirds, which is smaller than 3 halves. So is it clear what this thing is saying? Okay, and also I should say this is better than what we were getting from the Kováry-Sós-Turan theorem, except in the case k equals 2. Actually, in the case k equals 2, they kind of coincide. But so in the case k equals 2, right, it's kind of special because a cycle of length 4 is the same thing as k22. And actually, both of these things give the same upper bound up to the constant factor. So it's not terribly difficult to prove this theorem, but we're not going to actually prove this theorem because, there are kind of elementary nice proofs. In fact, there are nice proofs which give a much better constant than 100, like, giving a constant of like 8 or something like that, or 10. And actually, some of those are included in the list of project topics. But those proofs are a bit long. So what we're going to prove is actually a sort of easier statement, which uses some of the same ideas, but is a little bit easier to prove, a little bit shorter. So what we're going to do is actually, instead of forbidding just a cycle of length 2k, we're going to forbid a whole bunch of cycles. So, formally, if I have a set of graphs, curly h, so curly h is a collection of graphs, not just, it could be a single graph, or it could be, lots of graphs. So we can similarly define the extremal number of curly h to be the maximum number of edges in a graph on n vertices, which forbids all of the graphs in H. So it has no copy of any H in H. So what we're going to look at is what happens if I forbid all of the even cycles of length 4, 6, 8, 10, etc. up to 2k. And what we're going to prove is that the extremal number of this, is at most 2n times this thing. So n to the 1 over k plus 1. So in particular, it's big O of n to the 1 plus 1 over k. Okay. Is it clear what's going on? Yeah, exactly. So generally, if I took or suppose I have I forbid a family of graphs or something. And let's say I take a particular example from that family, or also I could take like a subset of it or something. That's going to be at most that, because so if I, basically if I have a graph which has so many edges that it must have a copy of H, then in particular it must have something in curly H because it has H. So that's, if you think about this maximum, or if you think about when you maximize over so the collection of graphs which don't have a cycle of length 2k is a bigger collection than the ones that don't have all of these things. And if I maximize over a larger collection, it gives me a bigger number. So upper bounding this thing is genuinely weaker than the Bondy and Simonovits result. But also you get a slightly better conclusion because there's no dependence on k here. The constant is just a constant, which doesn't grow with k. Whereas, like I said in Bondy and Simonovits' proof, you have 100k or something in front of this. So it's a bit of a trade-off. Yep. Okay, so before proving this, we're actually going to prove a couple of lemmas, which are also quite interesting in their own right. So the first lemma is that if I have any graph G, I want to prove that G has a bipartite subgraph with at least half the number of edges. So have any of you seen this particular statement before? Or does anyone remember seeing this before? Maybe it's probably no one has, but I don't know. And then secondly, does anyone have any idea how you'd prove this? Maybe that's too difficult to ask, but one kind of tricky thing here is that I know at least 2 proofs, and there could be more. So it could have something to do with it. There could be a proof that uses spanning trees, but I'm not sure. So maybe it wasn't a very well-formed question. But actually, the way we're going to prove this is actually something you've seen because you've seen it in this course. So the method we're going to use. So basically what we're going to do is just take the vertices of G, randomly color them red and blue, right? So each vertex, I independently flip a coin. For each vertex, I color it red if it's heads, blue if it's tails. And then inside of all the red vertices, we're just going to delete all the edges. And inside of all the blue vertices, we're just going to delete all the edges. And that's going to be a bipartite graph. Okay, and we want to say that when you do this, on average, half of the edges survive. And if on average half the edges survive, there must have been a way to do it so that half the edges survived. So let me kind of say that again, kind of a little bit more slowly. So here's the proof. So I'm going to partition the vertex set randomly into sets A and B. So you can think of A as being the red vertices and B as being blue. In other words, we flip a coin for each vertex. If it's heads, then we put v into A. Otherwise, put v into B. And like I said, inside of A, we just delete all the edges, and we also delete all the edges inside B. Okay. So how many edges survive this process on average? By survive, I mean they're edges that didn't get deleted. So if you think about it as coloring the vertices red and blue, right? We've actually kind of thought of this before. So if I randomly color vertices red and blue, and I look at a particular edge, what's the probability that that edge is like red on both sides? Yep, exactly. Yep. So probably 1/4 it's red on both sides, with probability 1/4 it's blue on both sides. So in total, with probability 1/2, it gets deleted. So therefore, on average, you have half of the edges getting deleted. So therefore, on average, you have half of them surviving. And if on average half of the edges survive, then there must have been at least one way to color so that at least half of the edges survived. So maybe I won't go into all the details here, but it's then just kind of linearity of expectation, right? So probability is 1/4, probability 1/4. Yeah. So then probability it survives is 1/2, and so you expect like on average for half of them to survive, but therefore like there has to be at least some choice where at least half of them survive. Otherwise, the average couldn't possibly be, if every way of coloring had less than half the edges surviving, then there'd be no way that the average could be so high, right? If I take an average of a bunch of numbers that are less than 100, then the average must be less than 100. You can also do this in a kind of there is also a kind of structural way of doing this. You could say, take a bipartition where you have, or a partition where you have maximized the number of edges across, and then you can think about like switching vertices over and stuff like that. But so I won't give you that structural proof, but that's another way to do it. And there could be other ways. Probably there are. Okay. So here's the second thing we need. So the first thing was we want to have a bipartite graph which has half the edges at least. The second thing we're going to use is this. So take a graph where, so just say first maybe, what's the average degree in a graph, right? Well, the average degree is the sum of the degrees over the number of vertices, right? Which is 2 times the number of edges over the number of vertices by handshaking, right? This is the handshaking lemma. So what I'm going to say here in this lemma is that, and this is kind of similar to what we did proving Erder-Stone. We're going to take a graph and we're going to restrict to a subgraph that has high minimum degree. And I claim that every graph has a subgraph with minimum degree at least equal to the number of edges in the original graph G divided by the number of vertices in G, which actually is half of the average degree of G, if you think about it, because the average degree is like that, because handshaking. So, I mean, it's not important that you necessarily, recognize that it's half the average degree, but it's maybe easy to remember the thing, I think. Okay, so we're going to prove this lemma next. Okay, so I take a graph and I want the minimum degree to be large. So it's not large, so I need to refine the graph to get a subgraph, but like what should I do? And this, the answer is the same as when we were doing Erder-Stone. I have a graph, I know nothing about the graph, except I know how many edges and vertices it has, and I want to get a subgraph with high minimum degree. What's the first thing I should do? Well, I better not delete an edge. That would not be intelligent, right? I may as well delete a vertex, and the vertex I choose better be a low degree one, because if I don't delete that one, I'm not going to get anywhere, right? If I don't delete a low degree vertex, my minimum degree is going to stay the same. Or it's going to even go down. So I better delete a vertex of smallest degree. Okay, so let's kind of analyze this thing again, but now we have a different kind of goal than before. So this time, we're going to prove this by induction on the number of vertices. The case where the number of vertices is 1, I want to find a subgraph with minimum degree, number of edges over number of vertices. If I've got one vertex, this is just 0. So I just take the whole graph, which has minimum degree 0. So let's now look at the general case where number of vertices is at least 2. Right, and we've kind of already answered this question, which vertex should we delete? It's the one with smallest degree. So, okay, one kind of silly thing is like if you already have minimum degree, at least the number of edges over the number of vertices, well, you'd be a bit silly to delete anything because it already satisfies the condition. So don't delete anything. Otherwise, take a vertex of the smallest degree, which is less than this value, our target value, and I let G prime be the graph I get by deleting deleting the vertex X from G. Okay, so we delete a vertex, we look at the smaller graph, G prime. And by induction, I know that inside G prime, I can find a vertex with, a subgraph inside G prime, which has minimum degree, at least like this thing, which is like half the average degree of G prime. Of course, I can't just erase the primes, right? Or else I'd be done. So I want it to be, I want it to be at least this value, but I've got G primes here. So we have to ask ourselves if this is good enough, right? Which is kind of the same thing as saying, is it true that the average degree of G prime is at least as large as the average degree of G? But let's kind of do this properly. So okay. So I want to prove, so just to be clear, I want to prove that this is at least my target value. Is it clear? And then I'll be done. So this is not a terribly difficult proof. It's simpler than the thing we did in Erdős-Stone. Okay. So what is this ratio? Yeah, that's right, I think, right? That's how many edges I lost. This is how many vertices I lost. What we knew is that the degree of X is less than edges of G over vertices of G. So we just plug that in and put a less or greater than sign. And it kind of works out magically, I think. I hope it does. Over vertices of G minus 1. Yeah. Wait, is that right? What happens when I factor out a E of G from the top? I get E of G 1 minus 1 over the vertices of G. Yeah. Which is the same as vertices of G minus 1 over vertices of G. So I'm just replacing what's in these parentheses. And then you can see that the vertices of G minus 1 cancels, and you're left with this. So therefore, you can always find a subgraph with minimum degree, at least this, because basically if you look at where you start, is the minimum degree at least that? If not, delete the smallest degree vertex and apply induction. And this calculation shows that the induction works, if that makes sense. Is that clear? Okay. In fact, it gives you a strict inequality, but we're not going to use that. Okay, so let's go back to what we wanted to prove. So remember, what we want to prove is that the extremal number of this, the collection of all the short even cycles, so even cycles of length 4, 6, up to 2k, is at most 2 times n to the 1 over k plus 1. Okay, let's go by contradiction. So suppose that you have a counterexample. So a counterexample is a graph G with n vertices, with no copies of these cycles, and which has more than this number of edges. Okay, right, so we want to apply these lemmas. So first I'm going to take G, and I can restrict it down to a bipartite subgraph, which has at least half as many edges. So G has a bipartite subgraph. So it's at least half of this, but here I've got a strict inequality. So I can get a bipartite subgraph with greater than n to the 1 over k plus 1 edges. And then I can apply my second lemma to, so does it matter which order I apply these in? Maybe it doesn't, but so I first go to a bipartite subgraph, and then I'm going to take that bipartite subgraph and find a subgraph of it which has high minimum degree. So this bipartite subgraph has a subgraph with minimum degree greater than however many edges it had divided by how many vertices it had. And the bipartite subgraph has the same edge set as G, right? It's just randomly split the vertices or whatever. So the minimum degree is going to be this number divided by n, which is n to the 1 over k plus 1. And of course, a subgraph of a bipartite graph is still bipartite. So now inside of G, we've found a bipartite graph with minimum degree greater than n to the 1 over k plus 1. Maybe I think I probably only need the greater than or equal to here, but let's not worry about that. Okay. So is it clear what we're dealing with here? We're now just going to focus on this subgraph. We're kind of throwing away a lot of G and just dealing with this. So this is just repeating what I just wrote. And okay, let's call this the final graph we get, like when we do both of these processes, we go to a bipartite graph, then we find high minimum degree. Let's call the final graph G prime prime. So what I'm going to do is a kind of breadth first search. So everything above this line is just mentioning the kind of properties we have. So this is all just a recap. Okay, let's do a kind of breadth first search inside of G prime prime. So what do I mean by that? Well, I just mean start with some vertex, which we call V naught. So we start with this V0, V naught, whatever. I'm going to define L0 to just be that vertex. That's kind of my 0th level of the search, or whatever. I'm going to let L1 be the neighborhood of V0. And then for each I, basically I let Li, like the ith level, is the neighborhood of the I minus 1th level that we haven't already found, right? All of the things that are neighbors of the I minus 1th level that are not in the previous levels. Okay. And actually it's good enough to just say it's not in the I minus 2 level. That's good enough. But because it can't be in a previous one because anyway, the distance, basically Li is the things that distance I from V0. Actually, that's probably the best way to say it. So Li equals distance, vertices at distance I. Maybe that would have made my life a lot easier to just say that. Okay. So all the vertices at distance I. Okay. So here's a kind of picture. Okay. How big is L0? Put this one to the audience. Maybe a silly question. 1. Okay, good. How big is L1? So I want a lower bound, not an exact number, but a lower bound on L1. Yep, because that's what I got for the minimum degree. And now what about L2? Something like, yeah, probably something like that. Well, okay, so we have to be careful about something here. So how are you getting any bound on this in some sense? Because in theory, maybe everyone in L1 has the same neighborhood in theory, but they can't, because if you think about it, if I take two vertices in L1, in fact, they can't even have a common neighbor in L2, because if they did, what are we going to find? We're going to find a 4 cycle. not quite triangle free, okay? But it's 4 cycle free. And this would be 1, 2, 3, 4 cycle. So basically, if I look at all of these, all of the neighborhoods of these vertices into the next level, they're all disjoint. Okay, of course, they're not disjoint in total because all of them are adjacent to V0. But if I look at their neighborhood into the next level, they're all disjoint. And the number of neighbors they have in the next level, each of them has at least this many neighbors in the next level because I don't count the neighbor V0. And there's at least this many of them. And if you think about it, it kind of continues on. So if I take two vertices here in L2, if they had a common neighbor here, I could follow them kind of backwards down to V0. You could kind of follow them down to V0 and find a 6 cycle. Or maybe they have a common neighbor in the previous level. But that's just as good because that's a 4 cycle. So if K is at least 3 and we're also forbidding 6 cycles, then actually two vertices in L2 can't have a common neighbor in L3, because if you kind of go from their common neighbor down to them and then trace it back until the first time that they meet below, that's going to trace out an even cycle. Oh, and actually, there was something mentioned about triangle free, which I actually that was actually a very good comment, because I've completely forgot to use the bipartite condition. Right, this graph is bipartite because we turned it into a bipartite graph. So there's no edges here inside of L1, because that would make an odd cycle. Right, there's no edges in here. So actually, genuinely, each vertex has all of its neighbors go up except for the one that goes down. Right, every neighbor has a unique neighbor in the previous level, and yeah, and the rest of them go up. There's no neighbors in the same level because there's no odd cycles. So basically, well, not even basically, exactly what you get is that the size of Li is n to the I minus 1 over k times n to the 1 over k plus 1, or it's at least this big. And so in particular, if I look at the last level has size at least this. But of course, the last level, so the number of vertices is at least as big as the last level. So the number of vertices in G or G prime or G double prime, whatever, is at least this, but that's greater than n. Contradiction. Basically, because you have no even cycles, you have a lot of expansion. Okay, that's the kind of idea. Every level expands a lot, and once you get to the kth level, it's so big that it's bigger than, like, it would have to be bigger than the number of vertices in the whole graph, but that's a contradiction. So this graph could not have existed. So I'm not sure if that's completely clear, but I think we're out of time. I'll just maybe say just 5 seconds about whether this is tight. So it's conjectured to be tight. So there's a question about why there's even k levels. Could it end earlier? Well, there has to be k levels because basically it's because of the minimum degree condition. So every vertex has at least a large number of neighbors, and every vertex only has one neighbor in the previous level because there weren't any common neighbors from that level upwards. So yeah, everything, if you think about it, you will have to have more and more levels. I think you'll have to have k, but you have to think through it, maybe in a small case or something like that. But I think it is k. I hope. Yeah, because C2k free. Whether it's k or k minus 1, you have to do some thinking, but I think it's k. So Erdős and Simonovits conjectured that this thing would be tight, that actually you should be able to make graphs without any cycle of length 2k, which have n to the 1 plus 1 over k vertices or edges. This is only known for a few small cases. So k equals 2, k equals 3, and k equals 5. Weirdly enough, k equals 4, it's not known. So this is cycle of length 4, 6, or 10, but nobody knows about a cycle of length 8 or length 12 or any other length. So, which is very strange, but and it's based again on some sort of geometric constructions involving things like projective planes.